Hi everybody. So in this collection of supplementary videos, what I'm going to do is I'm going to try and go back and fill in some of the examples that weren't done either on the original videos that we did for these this section of work or in class. So it will be a bit patchy, so you're going to have to keep on your toes to figure out where the questions are that we're coming from. Try and always put the slide number in the bottom so you can see it. So here we're working on slide 264, and in the video we did this example 1, but we didn't do example 2, 3 or 4. So we're going to just fill in the gaps, basically like we would have done in a lecture. So in this example, we're just asked to write down the complex conjugate of the numbers given. So remember what it means to be a complex conjugate. What we do is we have the same real part. But there's a sign change on the imaginary part of the complex number. So part 3 is just 2 plus 5i. Part 3, don't forget this is 0 plus 3i. And the complex conjugate of that, the real part stays the same and the sign changes on the imaginary part. So this is just minus 3i. And in part 4, the number is 4. That's just 4 plus 0i if we're working in the complex number system. And so that's 4 minus 0i. And so nothing changes, so it's just 4. Okay, so that's the first part of the supplementary work. The next example that we haven't done is this one on slide 267. So we're looking at the solutions of this quadratic, but you'll notice that the quadratic is one that's written in terms of z. And so we're putting that equal to 0 and we're trying to find the solutions. That is, the complex numbers z, such that if I put them into this, the left-hand side of this equation, it will make the whole thing 0. So what z's are going to have that property? Well, we're going to use the quadratic formula. So it's z equals minus b plus or minus the square root of b squared minus 4ac, and c is 10, all over 2a. So our a is 1. So let's simplify that a bit. 6 plus or minus the square root of minus 4 over 2. So this is 6 plus or minus 2i over 2. So it's 3 plus or minus I. Okay, so they're the solutions. So by now we've done a lot of further work on complex numbers, so you'll know to expect 2 solutions to this equation, and we want to plot the solutions in the complex plane. So here's 3 plus I. So this is 3, so this is the real axis, this is the imaginary axis, this is I. So that's the first one, Z1. So Z1 is 3 plus I, and Z2 then is 3 minus I. So it's down here. So that's my point Z2. So what do you notice about the relationship between those solutions? Well, they're complex conjugate pairs, and you will know by now to expect that if you had a solution to an equation like this one, its conjugate will also be a solution, because you're getting this term here plus or minus the imaginary part. And of course, so when you simplify it, it's 3 plus or minus the imaginary part, and that's what we mean by a complex conjugate. So if we have the complex conjugate of 3 plus I, it's just 3 minus I, and if we have 3 minus I, the conjugate is just 3 plus I. So the fact that these solutions will always come in complex conjugate pairs is true no matter what quadratic we have if if you solve it over the complex number system and you get a complex solution. The next example we're looking at is on slide 268, and you'll have to bear with me a bit on these solutions to these problems from the lectures, because it's a little bit hard for me to tell from my notes which ones we did and which ones I put up in class and which ones I didn't. So we certainly did this one on the video. If you've seen these before, then you can skip through them. If you haven't seen them before, then we'll go through them one by one. As I said, I can't clearly tell which ones I did in the lecture or not. So let's start off with part 2. We're letting z be equal to x plus iy, so it's just some arbitrary complex number, and so z bar is x minus iy, so that's the conjugate. And what we want to do is look at z minus z bar. So z minus z bar is equal to x plus iy minus x minus iy, and that's just x minus x plus iy, and that I've got a minus minus there, so I've got a plus iy, so this becomes 0 and I get 2yi. So you can see that it doesn't matter what x and y is, provided y is not 0, of course, then this is going to be an imaginary number. The x terms, the real part cancels out, and you just get left with the imaginary part. What about z times z bar? So z times z bar, we're looking at x plus iy times x minus iy, and we're just going to multiply those out, and you'll be used to doing this by now. So I get an x squared term, I get a minus xyi term, I get an plus xyi term, and I get a minus I squared y squared term. So these cancel out. This is an x squared, and I squared is just minus 1, of course, so this is just plus y squared. And you can see that that's exactly what was predicted here. Z times z bar is a real number, so you can see that the imaginary part of this is 0. Now, you'll know by now that this is the sort of thing we've been using in complex division to make the denominator of a complex number real. So in this next example, this is the one from the previous page, I've just transferred it over here, we're trying to show that these two expressions are equal. And basically this says that when you're taking the sum of two complex numbers, z plus w, and then taking the conjugate, it's the same as if you'd taken the conjugate of each one separately and then added them after. So this is basically saying something about the order of operations. And what we do with an example like this one is just work on each side separately and then show they're the same at the end. So we're still going to let z be equal to some arbitrary complex number and w is equal to some different arbitrary complex number. And then we're going to do both of these things separately. So let's start off on the left, and we're looking at z plus w bar. So z plus w is x plus I y plus a plus ib, and so we do that sum first and then we take the conjugate. So this is x plus a, so I'm just collecting the real parts together, and I'm collecting the imaginary parts together, and I need to take the conjugate, so that just changes the sign on the imaginary part. So this is x plus a minus I y plus b. On the other hand, we have to look at z bar plus w bar. So this is x plus I y bar plus a plus I b bar. So this says do the conjugate first and then do the addition. So if I do the conjugate here, this is x minus iy, and then I've got plus, and I'm doing the conjugate of this, so this is a minus ib, and now I'm doing the addition. So this is x plus a plus minus iy plus minus ib, and it's got a, I can take the minus I outside, so this is x plus a minus I y plus b, and you can see that the expression here is the same as this one, so we showed that result. But I hope you noticed that the difference in the left hand side and the right hand side was the order of operation that we did. Okay, so there's one more left to do in this section, and that's the product now. So again, this is saying something about the order of operations. Here we're multiplying the numbers together first and then taking the conjugate. On the right hand side, we're taking the conjugate of the number here, the conjugate of w, and then we're doing the multiplication after that. Okay, so let's start with this one, zw bar. So this is x plus iy times a plus ib, and then I'm taking the conjugate. So I have to do the multiplication first. So this is going to be x times a plus I x times b plus I y times a plus I squared y b. Okay, so xa is a real part of this expression. I squared is minus 1, so this term is minus yb, and then these two terms have both got an I, so this is I times xb plus ya. Okay, so that's what we get on the left. What about on the right? I have to take the conjugate first, and then I'm going to multiply them together. So it's x plus I y bar times a plus ib bar. So this is x minus iy times a minus ib, and now we just have to multiply out. So this is x times a minus ixb minus iya. Two minus signs together gives me a plus, and then I've got an I squared yb. So this is xa, that's minus 1 now, so it's minus yb minus ixb plus ya. Okay, so let's just check. They should be the same. They are. So job done.